today we're going to do a lab, a circular motion lab, the purpose of which is going to be to find a relationship between a couple of variables within that circular motion equation, that centripetal force equation. The procedure, if you need a little bit more than what I'm explaining, what I'm discussing in class here, you can go back and look at page 245 and 246 of your textbook. It's there. Having said that, when you go to write this up, you're going to write everything up except the procedure. So you don't need to recopy that because it's almost exactly the same as it is in your textbook. You need to refer to it, go ahead. The problem is exactly phrased in the form of a question. For an object moving with uniform circular motion, what is the relationship, right? Phrased in the form of a question. What is the relationship between the radius of the object's path and its speed? What's the relationship between r and v? We have three variables here, or three sets of variables at least, the manipulated, the responding, and the control variables. What do you think the manipulated variable would be based on the problem? Based on the problem. What's the relationship that exists between the radius of the path and its speed? Yeah, the radius of the path. You're changing the radius of the path. What responds to that? What changes because the radius changes? At least what potentially changes because the radius changes? The speed. What are the control variables? Well, I'm not going to tell you what the control variables are. You're going to have to look through this yourself and identify the control variables. There's a few of them here, so it's good, especially in this activity, but in every other activity for that matter, as you're going through it, to notice those things and write those things down on your piece of paper, just so that when you're going back to write it out, you don't forget, right? When you're 2 or 3 days removed from it, okay, you don't want to forget that. So let's get the control variables as well, okay? Now, what's the procedure look like? I'm going to discuss it with you, but again, if you want to go back and look at those pages of your textbook, then by all means, you can go ahead and do that. We've got an apparatus for every group here that consists of a PVC tube that's cut into a length of about 15, 20 centimeters. Doesn't matter exactly how long it is. Threaded through that tube is a string. On the end of that string is a rubber stopper. You can see right now as I hold the real one up in my hand here that the string isn't attached to the PVC tube. Okay, it's free to go. If I let it go, it almost falls right out, but there's a little knot there that kept it from falling out. Essentially, though, it's free to move, right? There's a rubber stopper on the end of it that I'm going to swing around. Right now, I don't want to swing this around because if I do, what's going to happen? The radius is going to change, yeah. But if I'm not holding it at the other end, what's going to happen? If my hand isn't there to provide a centripetal force acting on this rubber stopper, if there's no centripetal force acting on the rubber stopper is going to go off in a straight line, right? So we need something to provide a centripetal force. It's not going to be our hand because we can't control that very well. Okay, we can't keep that constant. Do you hear what I just said? We can't keep that constant very well. We need something on there to keep constant. So what we're going to do is attach a mass on the end of it. Now the procedure uses a mass of 100 grams. You're going to be given a mass set with a whole bunch of different masses. I would suggest that you start off with 100 grams. If you find that's not working for you, then you can switch it. But if you switch it, you got to start again. That makes sense? Because you need that variable to stay the same throughout the entire experiment. Okay? You need that variable to stay the same throughout the entire experiment. Okay? So what are we going to do exactly once we have that 100-gram mass hooked on the end of this? You can see that I'm holding this now with the mass attached to the end of it. By the way, don't swing it the other way so that the steel mass is the one that's being swung and the rubber stopper is hanging through. Okay, if something falls off, and we hope that doesn't happen, but if something falls off, we want it to be the rubber stopper, not the 100-gram steel mass. Okay, so we swing it around. As you swing it around, you notice that swing it faster, okay, it changes the radius. Swing it slower, okay, it decreases the radius, and so on. We need to keep it at a constant speed. We need to keep it at a constant speed and, for one trial, a constant radius. That's going to take a little bit of practice. Okay, somebody in your group is probably going to be better at it than the others in the group. Find the person that's the best at swinging this thing around and keeping the radius constant. Now, how do you know if the radius is constant? Well, what you're going to do is mark off distances. Many of these are already going to have the distances marked off. Okay, but you're going to want to double check to make sure that the group that used this before you last year or in Mr. Godair's class didn't mark off the distances wrong. You're going to want to start off with a distance of 20 centimeters. Actually, mark it off every 10 centimeters. So 10 centimeters from the rubber stopper, 20 from the rubber stopper, 30 from the rubber stopper, 40 from the rubber stopper, 50 and 60 from the rubber stopper. You want to have, well, 6 different radiuses starting at 0.2. You might want to mark off 0.1 just so that you know. Okay, it doesn't really matter. 6 different radiuses starting at 0.20 meters. You're going to mark them off with a Sharpie so that you can clearly see where that mark is. Got it? As I start swinging this around, okay, right now this is 30 centimeters, this one right here. Okay, as I start swinging this around, okay, I want to swing it so that that 30 centimeter mark is exactly at the top of the PVC tube and isn't increasing or isn't moving like it just did when I increase the speed. That make sense? It is going to take a little bit of playing with. You're going to find that when you first start this, oh, I didn't keep the radius constant. Stop. Try again. Okay, keep practicing, keep playing with it until you manage to keep the radius the same at, for the first trial, 20 centimeters. Then what I want you to do, or at least what I want your group to do, is to time how long it takes to make 20 revolutions. So right now I'm at 30 centimeters. Okay, 30 centimeters. One of your partners is going to count the number of revolutions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Count to 20 revolutions. Time that. Okay, write down how much time it took to go around 20 times. Somebody in your group is going to swing this. Somebody in your group is going to watch to make sure the radius is remaining constant. Somebody in your group is going to count the number of revolutions and time how long it takes for 20 of those revolutions. That make sense? Write down that time. And then do it again. Hopefully you get the same time. If you don't, well, that's the purpose of doing 2 trials, so that ultimately we can average them together and get hopefully a little bit better of a result. That's your data. That's it. Here's your analysis. Looks kind of complicated, but it's actually not that bad. The radius you've already got, right? 0.20, 0.30, and so on, all the way up to 0.60. Your time for the revolutions, you've already got that. That was part of your data. Now your average time, hey, that's easy, right? How do you find an average between this number and this number? Add them and divide by 2, right? So we're going to say T1 plus T2 divided by 2. The period, that's a little bit trickier. How are we going to find the period? Big T. It's your average time divided by, we want the time for 1 revolution. We just measure the time for 20 revolutions. The period is going to be the time for 20 revolutions divided by 20. So take whatever time you get right there, divide it by 20 to get the period. Now, speed is going to be 2 pi r divided by t. So you're going to say 2 times pi times 0.2 in this case, divided by t, the period that you just calculated. Okay, fill it in. Then keep going through that, doing the same thing for all the rest of your trials, all 5 of your trials. If it was me, hey, I'd do this on Excel. If it was me, I'd enter this number on Excel, these numbers on Excel, I'd enter these numbers on Excel, I'd enter these numbers on Excel, and then I'd have Excel calculate all these numbers for me by entering a formula here, a formula here, a formula here, and then copying those formulas down to my other cells. You need a little bit of help with that, I can help you with how you'd enter that formula, okay? Then what are you going to have to do? Well, there's a lot of analysis questions that are in your book, but I've circled the 2 that you really got to focus on, because in the end, most of those analysis questions you've already done. When you did your table, you did those analysis questions. I want you to specifically do question 5 and 6. Okay? Of course, you got to do them all, but it's for the most part a part of what you've already done. I want you to separately do question 5 and 6. Identify the force that acted as a centripetal force and determine its value. And then, number 6, plot a graph. So that comes next. Okay, that comes next. Plot a graph of velocity versus radius. That shouldn't actually say velocity versus radius. What should it say? Speed versus radius. Okay, speed versus radius. So that graph is going to look like this. Not going to tell you what the shape is. You're going to determine from that shape what the relationship is. Okay, what the relationship is. In other words, as R goes up, V goes up linearly. As R goes up, V goes up exponentially. As R goes up, V goes down, whatever the case may be. Okay, whatever you find on that graph. If you have trouble interpreting it, I'll help you. Then your conclusion, then your sources of error, and then you're done. So what do you got to hand in here? Problem, variables, hypothesis, data, analysis, conclusion, sources of error. What's conspicuously missing here? The procedure. We don't need a procedure. I don't believe in just making you rewrite something that you're following to the letter from something that's in the textbook already. There's no point in doing that, I don't think. So we're not going to make you rewrite that procedure, but I do want you to do everything else there. Yep.